Hi everyone, and welcome to the third in the series of LimitState webinars for 2017. I'm Tom Pritchard and I'm your host for today's event. I'll be introducing you to Professor Matthew Gilbert shortly, who will be talking about how you can use yield line analysis to reveal hidden reserves of strength in reinforced concrete slabs. Today we're going to aim to show you how the yield line method has been systematically automated, removing a lot of the uncertainty that the critical pattern has been missed, and how LimitState SLAB, our yield line software, can be used to rapidly analyse a reinforced concrete slab and often demonstrate that the additional capacity is there when compared with other methods. I'll also be demonstrating a little more about the features in LimitState SLAB in a practical demonstration. The presentation part of the webinar is due to last about 35 minutes, and there'll be around 5 minutes at the end for questions. If you do have some questions, then feel free to put them in the chat functionality or the question functionality that should be there in front of you, and we'll try and get round to them at the end. Obviously, with it being quite a short webinar, we don't always have time to get round to all of them, but we will try and get round to answering them via email afterwards if there are questions that we don't actually manage to address. On the subject of questions, if you do have any after the webinar, then please do email us on info@limitstate.com and we'll be happy to speak to you in detail about it. So without further delay, I'd like to welcome you to our speaker for today, who is Professor Matthew Gilbert, and he'll be talking about the methodology of automating yield line analysis. So I'll now pass you over to him.
Thanks very much, Tom, and thanks very much everyone for joining us for the webinar today. So what we're going to be looking at is applying a method which is able to identify collapse mechanisms in slabs of arbitrary geometry. It's a tool that only relatively recently been made available, and what it basically does, as Tom mentioned, is systematically automate the yield line method. So we can look at the pattern of yield lines for a given slab, geometry, loading and material properties, and we can also get a visualization of the collapse mechanism just to help interpretation, so we can understand as engineers what's going on. Okay, so I'll just say a few things about LimitState before we get into the meat of the presentation. Actually, it's been around for slightly more than 10 years now. It's spun out from the University of Sheffield in 2006. It's basically charged with commercializing academic research, making research methods that have been developed in the university available to a wider audience. What we do is we use methods that are not used in mainstream analysis software, and we make sure the software is easy to use, robust and well validated. The main priority, certainly the initial priority of the company, was on developing tools which effectively fill the gap between traditional and advanced analysis tools. So if you look at, for example, geotechnical analysis as an example, there are hand analysis tools which have typically been automated in spreadsheets or in simple software applications. And then at the other end of the spectrum, you have methods based on, for example, nonlinear finite elements or discrete elements, and you have a large gap between these two types of tools. The problem with traditional tools is they're very often quite narrow in their range of application, or they make assumptions which you may not be particularly happy with for a given real-world problem. So we fill that gap with numerical rigid plastic analysis tools, and what they basically allow you to do is to apply some of the relatively simple methods to a much broader range of problems, and broader in the sense of, for example, geometrically more complex with arbitrary distributions of material properties, etc. And we could be talking about geotechnical problems, masonry problems, or obviously the subject of today's talk, concrete slab analysis problems, where we can very rapidly identify a yield line pattern and associated load or load factor. So three main tools LimitState have developed over the last few years: LimitState Ring, LimitState Geo and LimitState Slab. Those tools now widely used in the UK, Europe, and in the wider world as well. So here's a list of just a few of the companies that are using LimitState software. So some big names in there: AECOM, Atkins, Balfour Beatty, and so forth. Okay, so moving on to the subject of yield line analysis and how we might use this to reveal hidden strength. For those of you who are not familiar with the yield line method, it's a direct means of analysing a slab at the collapse state. So traditionally it was a hand method, so the user would guess a yield line pattern and then they would use the work method typically to calculate the load capacity. So you would equate internal and external work, and what you might need to do is iterate, so try a number of different collapse mechanisms, and what you wanted to do was to make sure that you had a safe result, so you would be choosing the lowest load factor or the highest required moment capacity, depending on how you pose the problem. Benefits of the yield line method: it's comparatively simple to do the calculations. You get the computed collapse load or load factor directly. There's no need to iterate. In the context of design, you can end up with very economical designs, or if you're using the method for assessment, you can end up with more realistic assessments of capacity, certainly, than elastic methods. The downsides: if you choose the incorrect mechanism, then you will end up overestimating the true capacity. Another downside is it only considers flexural failure, so it doesn't, for example, warn you about shear failure, and it doesn't provide information about deflections prior to collapse. The next slide just shows some of the potential benefits that you can get from using the yield line method. So many of you will be aware of this probably. We have seen over the years a gradual increase in vehicle loads. I think in 1964 the maximum capacity of vehicle was 22 tons. We now have to carry 44 ton vehicles. So many of the, for example, motorway bridges that had been designed to carry the lower loads were assumed not to be capable of carrying modern 44 ton vehicles. However, many of those early bridges were designed using elastic methods, and hence there was quite a lot of conservatism built into those bridge designs. So what this slide shows is a reanalysis of, in this case, 21 bridges carried out by Middleton and co-workers at the University of Cambridge. And what they were able to show was that even the elastic capacity for a bridge was very low, the plastic capacity would be significantly higher, and in many, many cases enough to meet the requirements. The way this was carried out at this time in the sort of 1990s and early 2000s was to try a whole sequence of different yield line patterns. There's a library of yield line patterns. So it looked very effective. The only worry is that if you've got a library of 27 mechanisms, when you go to a new unfamiliar bridge, can you be sure that one of those 27 mechanisms is critical, or is actually there a mechanism number 28 lurking which is actually more critical, which you miss? And obviously if you miss that, you will end up overestimating capacity. So from the point of view of design, again probably around the same time, there was quite a lot of work looking at the benefits of applying the yield line method to the design of concrete slabs. So there was a large-scale building constructed at the big hangar at Cardington, and what they found was that using yield line design they could end up with the lowest amount of reinforcement in terms of tonnage, but also comparatively simple arrangements, so only 22 bar marks compared with, for example, 75 or 76 with traditional elastic design. So you get a nice double benefit, little tonnage, low tonnage, and simple reinforcement detail. Buildings often have less regular shapes compared with bridge decks, so it makes using that library of potential yield line patterns quite problematic. If we could automate the yield line method so that it can be applied to general geometries, then we can apply it with confidence to buildings, and the benefits are that potentially we can indicate hidden reserves of strength. And that could be for reuse of an existing building. It could be during rehabilitation work of an existing building. For example, if you want to run plant over a slab on a temporary basis, or it could be during new construction. If it's an existing building, one of the benefits is that you can very often determine deflections using a load test rather than using methods to predict the deflections in advance, which can be quite crude. And clearly, if you can avoid strengthening works in an existing building, then the savings can be very, very large. Generally speaking, making changes to an existing concrete slab becomes expensive very quickly. Okay, before I go on to how it works, I'm just going to run the software for a few minutes just to kind of show you, how it works and how quick and easy it is, hopefully, to use. So when I start the software, I have option to describe the geometry of a slab myself, or I can actually read it in from a DXF file, or there's actually a couple of simple rectangular slab options in this new project tool that I could choose. So for example, if I choose rectangular slab, I can enter details of the project. I can enter details of the slab, for example, the geometry, whether the boundaries are, for example, fixed or simple. Let's make them simple just for simplicity. I can then choose to define a structural definition. So structural definitions would require knowledge of the reinforcement and the concrete and the thickness of the slab. For simplicity, I'm just going to use a default unit plastic momentary resistance material just at this point. Moving on to loads, we can specify self-weight loads, pressure loads, which is actually what I've got here by default, line loads or point loads. I'm just going to stick with the default pressure load. Keep the defaults for the analysis as well. Click finish, and then if I click solve, then what it will do is it will crank through and do the analysis, and it will also very rapidly just show me the deformed shape. Now this is exactly the same geometry as you would typically get using a hand analysis. Because we have a very simple problem, simple supports, rectangular shape, we end up getting something very similar. So what I want to do is just move on to something a little bit more challenging for the software. So I'm going to use the empty option in the new project dialog. I'm going to draw it. I'll keep the default grid. Obviously, if you know the sort of geometry that you're dealing with, you can choose an appropriate range. And I'm just going to draw pretty much by freehand using this this grid. I'm actually going to use the polygon tool. I'm going to just create a relatively simple geometry, but certainly more complex than a rectangle. So there I've got my geometry. It is just a geometry, however. If I want to assign a material, I can go to the create new structural definition dialog and create one, or for sake of simplicity, I can just drag and drop an existing one on. So this is the unit MP weightless material. I need to assign a set of boundaries. So what I can do is I can use this select tool, and in the property editor at the right hand side I can choose the external boundaries to be, for example, simple again. So I'm almost ready to go. There's one thing I haven't done yet is deal with the loads. So if I click on the add new load, I can simply select all and OK, and by default it's suggesting using unit pressure load. So for the time being I'll keep that as well. So now I have everything I need, and I can click solve, and hopefully I can get a solution. And the initial solution is nice and simple as before. However, I can very easily change the boundaries. For example, I could change the simple supports at these extreme corners to be fixed, and see if that affects the solution and the load factor. Now the load factor is actually given in the output. It's actually an adequacy factor, and that's a multiplier on the applied load at collapse. So if I click solve, it was 2.75, but by providing the fixed supports it's actually increased somewhat to 4.4, and again I can get a very nice view of this mechanism displayed. I'll just perhaps do one more thing before going back to the slides. Have something that's less elegant and symmetrical. If we, for example, change the top support to be free, and doesn't present any problems to the software, it can deal with any arbitrary boundary or loading conditions. And you see it's down again, the adequacy factor down to 3.3, and we've got a slightly more complex failure mechanism that would probably be quite challenging to analyze by hand, and hence you would be very also you wouldn't be like to actually find this particular mechanism. You'd probably have an approximate idealization of this, and you'd end up with a degree of non-conservatism there. Okay, so if we just turn to the slides, just a few words about how the automated yield line method works. The main enabling technology is something called Discontinuity Layout Optimization, or DLO for short. It's a rapid and direct means of identifying the critical yield line pattern. Details of the method were published in publication in the Proceedings of the Royal Society in 2014. It turns out the problem is a simple linear optimization problem from a mathematical point of view. So that means it's easy to solve, which is why we get solutions very, very quickly. The steps in the process, you start with a slab. We've given geometry and boundary and load conditions. In this case, we've got let's say we have a distributed pressure load. What we do is we discretize that with nodes. We then connect each node to every other node with a potential yield line discontinuity, and then we use optimization to find the optimal subset of discontinuities which describes the yield line pattern. In this case, we've got a relatively coarse discretization of nodes, so we end up with a relatively simple yield line pattern, and one which will be slightly non-conservative, so the solution will be slightly higher in terms of load factor than the true solution. In terms of the mathematics, what we're basically doing is minimizing energy subject to nodal compatibility constraints and a imposed unit displacement. So using the theorem of virtual work, we can formulate it in this manner. One of the key aspects is nodal compatibility. what basically we're doing at each node, such as the one at the bottom left-hand corner, is resolving the rotations in the x direction in the top expression and in the y direction in the bottom expression. And it's analogous to when you're doing a truss analysis and you're resolving forces, basically. So there's an analogy between truss layout optimization and slab yield line pattern optimization. And if you want to know more details, there's actually a more user-friendly description of the method down in the Royal Society paper in the October 2015 issue of the Structural Engineer magazine. Okay, just crunch through a few examples. Simple square slab, so you get the solutions that you expect. So for a simple square slab with simple supports and a distributed load, then you end up with just a sort of an X pattern. If you have uniformly distributed load and a fixed supporting boundary, then we have these corner fans identified automatically using the method. So there's no nothing special we need to do. The software, because it's minimizing energy, it will automatically show that that's more critical than the mechanism shown on the left. If we have a point load in the middle of the slab and we move the pressure load, then we end up with this kind of bicycle wheel or fan type yield line pattern. Again, that's identified automatically. People have tried to automate the yield line method in the past and they've struggled to identify these kind of features. And obviously we can also deal with more complex geometries, such as the one shown on screen now, which has got a central hole and it's got a variety of different support conditions. This particular one is in the literature, and we're able to find a solution which is better than any other solution put forward in the literature, because the method successfully automates the yield line method. And if we have lots of nodes in the problem, we have very, very, very close approximations of the exact solution. Moving on to a more practical example, this is a apartment block in London, and it was actually the slab for this apartment block was actually designed using yield line method, and it was actually documented in design guide put forward by the Concrete Centre 10-12 years ago. And what they did in their design guide is document the yield line mechanisms that they needed to consider during the design of this slab. And so if you look at the right hand side, you can see lots of individual patterns tested by hand. We've actually got his blade columns in the interior of the slab, and so we've got these kind of classic X or slightly more complex patterns shown. The one that they found to be most critical was actually the one on the left-hand side, which is kind of a folding plate mechanism. But the time involved in actually investigating all these mechanisms would have been, quite significant. With the software, all you need to do is get the geometry in and press a button, and a few seconds later you will see the yield line pattern. And in actual fact, the pattern is quite close to the folding plate mechanism that was suggested. It's a little bit more complex. It actually intrudes a little bit more into the interior of the building than was proposed, and so the hand-based method was, I think, about 8% non-conservative in this particular case. However, the people who did that yield line analysis were very skilled and expert, and there's always a worry with people who are new to the yield line pattern the yield line method, that you may miss the critical one. And I think that has limited its usage in recent years. The automation that we've just looked at effectively obviates that issue and allows us to directly analyze yield line patterns and identify the critical one. Okay, what I'm going to do now is hand over to back over to Tom, who's going to talk you through some hands-on usage of the software.
Thanks, Matthew. So as Matthew said, I'm just going to take you through a few little demonstrations of the software just to show you some of the things that you can do with it. So we'll go back into it, and what I'll do is build up a problem and start making some changes to it. So one thing that LimitState SLAB is good for is doing sort of Whatif analysis, so looking at different scenarios, quickly assessing the critical yield line pattern and associated adequacy factor. So what we're going to do is go back and start with the default rectangular slab problem and go through, start with a 5x4 meter slab, and in this case, instead of having fixed supports all the way around, what I'll do is just make them all simple. As you'll have seen, there's a choice of a few different boundary conditions, and we'll explore those in a little more detail shortly. So we've got our geometry, we've got our boundary conditions. I'm going to make a structural definition. I'll keep it as the standard isotropic one to start with, but I'll change the color just to make sure that we can differentiate that in the structural definitions on the left hand side here. So we've got that. In terms of our weight, we'll just have the unit pressure again, and a medium nodal density, just so that it will solve quickly enough for me to be able to talk over it. So here we go, it's gone through, it's solved already, and very quickly what we can see is that it's identified this envelope shaped failure mechanism with an adequacy factor of 0.615 on it. Also, what you can see is also that we can animate it. I think Matthew may have mentioned that previously, and also if we want to report, we can select that from the analysis options, and we can see that we can output a report, so we can pass that over to our clients or whatever. So like I say, what we want to start doing is looking at different things. So the first thing we might want to think about is perhaps our slab definition, instead of being an isotropic material, maybe want it to be an orthotropic material, so we can very easily just select the definition in the left hand side there and change the properties in here. So I'll change the hogging and sagging moment capacities from 1 to 5, and we can solve again, and we will see that again it's coming up with something akin to an envelope failure mechanism, but this time, because we've got the orthotropic material properties in there, the sort of widthways yield line is longer than it was previously, and our adequacy factor has gone up from what was, I think, 0.6 to 1.88. So very quickly just make changes like that. Another thing we may want to do is to add in a column or something like that. So what we can do is, what I'll first do is take the material back to being isotropic and turn on the grid, and we say, okay, maybe we have a column in there somewhere. I'm going to put one around the 2.2 mark within our slab there, and very quickly delete that center part, select all the boundaries around the edge of this space that we've opened up, and set them, in this case we'll set them to fixed. You can also have them as simple, obviously. And now we've done that, what we can do is to solve the problem, and this time what we're seeing, again, very quickly the failure mechanism is identified, and in this case it's something that will be quite difficult to conceptualize and also analyze manually, but within a few seconds the software has identified it. What we've got is a combination somewhat of an envelope type failure mechanism towards the right hand side, plus, because we've got this column, a fan type failure mechanism emanating from there. So it's a combination of the two things, and again, because we've put this column in, we've got an adequacy factor of 1.3. If we compare it to the 0.6 that we got for the situation without the column, then we can see what effect just having that column in there does. So one of the things we may want to do is, okay, we've got a column there, perhaps we want to move it slightly to the left and see what happens if it was over there. So again, we can put on our grid, we can drag the column across and solve again and see what the effect is of doing that. And again, within a couple of seconds, we've got a critical failure mechanism, and this time it's the adequacy factor is only just above 1. So if we are in a position where we got the partial safety factors that we wish to apply to the problem are actually included in the calculations, then we would know that this particular configuration was just on the safe side. So we've added this column in. Maybe what we want to do is see what happens if this right-hand boundary, instead of being simply supported, is actually free. And what we could do is just change the boundary conditions again, and we can see almost immediately that the failure mechanism has changed from being one of a sort of combination of an envelope and a fan to actually being a fan that's attracted to this free edge along the right-hand side here. And maybe just last for this one, what we're going to do is take a look at what happens if we then apply some propping force in the form of a column to this right hand side. Again, if we can just select those boundaries, make them simple and solve, and again see what the change in the critical failure mechanism and the associated adequacy factor is. So in this case we've gone from 0.57 up to 1.03, so almost doubling the capacity of that slab just by having that column there. And as I said previously, these are all things where we're very quickly making changes, but they're identifying critical failure mechanisms that are would be somewhat difficult to conceptualize and also calculate by hand. So something else that we may want to do is look at slab liftoff over the top of support. So I'll start a new problem. We'll start off with a rectangular slab, and in this case we'll have instead of a rectangular one, we'll make it square, and again we can have simple supports around the edges. Everything else we'll leave as default, so default material properties, default loading, that sort of thing. So we just got a pressure load on there, and if I solve, what we'll see is that we get the sort of classical cross-shaped failure mechanism there, and if I animate, we can see that we've got sort of hugging and sagging as we would expect. So the next thing we want to be looking at is whether or not liftoff and considering that around the edges is going to affect this particular problem. So if I just unlock, what I can do is select all the 4 edges around the external boundaries. We can see in the property editor here on the right hand side that we've got a field for support liftoff. If I just change that from false to true and solve again, we can see previously our solution, our adequacy factor was 24. If I solve now, we can already see that the adequacy factor has gone down to 22.2, and if I zoom in on the edges here, we can see that actually the slab has come away from the supports at these edges. So we've got a small amount of liftoff in these corners, and our failure mechanism, instead of being the traditional sort of cross, now we've got more of a radial arrangement of yield lines. So we've got the liftoff and the potential for that. Other things we can do is set a degree of partial fixity to the edges. So what we can do is if I select a boundary, excuse me, yeah, so if I select all 4 external boundaries, change the support type to partially fixed, what we can see here is that we get a support strength ratio. So in our case here, what it's saying is that for all of these edges, they're going to be fixed until, I'll just select that back again, until such a point where the MP value is 50% of the surrounding slab. So in what we've got in here, which I think is the unit MP. So when it reaches an MP of 0.5, then that support is considered to not be active anymore. So if we solve again, if you remember previously, what we had was the classical X-shaped failure mechanism. What we've got here now is one with sort of the fans in the corners again, and our adequacy factor here has gone, because it's fixed rather than simple, our adequacy factor is 34. If I unlock it and change that now to 1.0, so it's basically fully fixed, we should be able to see that the adequacy factor has gone up, and we've got a much more traditional failure mechanism with fans in the corners there. And the last thing I think I want to show you is potentially just having a knife edge support. So what we can do is very quickly make a new rectangular slab, and if I remove the support from the top and the bottom and make that free, what we could do is solve this problem, and what we'll get is just a single line. So we're getting sort of folding book type failure mechanism for this particular problem. But maybe we want to provide a support that could come from a wall or something in the middle, and it's relatively easy to do that. All we do is draw a boundary internally, select that boundary. We can see we've got a support type here that we can change to knife edge, and that just means that the slab is allowed to pass over the top of this support, so it's restricted from movement in the vertical direction, but rotations are continued across the top of it. So if I solve the problem again now, we've moved from a single book type folding mechanism to a double one with this support across the top there. If I make that right hand side free, so we've got a big lever on the right hand side of the problem, as we'd expect, what happens is that the problem folds over the top of that knife edge support. But what we can very quickly do is just select it and move the position of it. So if I make the position of that boundary as x equals 3.75, so move it a quarter of the way across to the right hand side and solve again, what we'll see is that we've got this fold here, but the slab is continuous over the top of this knife edge support, and it doesn't actually have a yield line at that point. It passes across the top. So hopefully that's given you a sort of flavour of the functionality of LimitState Slab and some of the things that you can potentially do with it. What we'll do is just go back to the PowerPoint and go through some of the conclusions. So my saying is that the yield line method provides a powerful means of analysing the ultimate collapse limit state. It can reveal hidden strength in existing slabs, or that if you're looking at a new slab, it requires less reinforcement than maybe suggested by elastic analysis methods. However, up until now, the general lack of implementation has meant that there has been limited usage of the yield line method in recent years. The yield line method has also been automated via discontinuity layout optimization, which typically involves a linear optimization, which is easy to solve, and it allows you to identify things like fan type mechanisms and others automatically. And obviously, as we've demonstrated, it's the DLO method of yield line analysis has been incorporated into LimitState Slab. So what we'll do now is just have a look and see if there are any questions. If you bear with me a second, I will have a look, and there may be one or two. So first question is, if the slab thickness is in different panels, can it be, if it's variable in different panels, can you vary it within the software? So yes, what we can do, if I go back to the problem, actually we'll take a look at this one. So we've got two separate panels here. What we could potentially do within our structural definitions, you can see that there is an option for thickness, that is used for self-weight calculations, so in conjunction with the unit weight. And also what you can do is obviously have different values for the moment capacities in hogging and sagging for the different panels, and you could potentially, so I could put that across to the right, make that a zero strength concrete, and you could build up your model in that way. Have another look, see if we have any other questions. Yeah. Oh yeah, so as a follow-on to that one, they were saying, do we need to calculate the plastic moment capacity first and then add that in, rather than there's no way in the software to do it? And the answer is yes. So what you would do is look at the different sections of your building or bridge and then calculate the plastic moment and the direction accordingly and add that in as a structural definition. And now the third question, can we apply line loading? So obviously I think up until now all you've seen is the ability to have pressure loading, and the answer to that is yes. You can see the purple icons up at the top of the software here are sort of identifying the different types of loading you can have. So we can have point loading, line loading and pressure loading. What I will do is I'll start on a new problem just to make sure that everything's okay. So in this case, if I click on the load case manager, you can see that we've got self-weight loading and pressure loading on there. If I want to then add a line load somewhere along there, it's a case of just clicking that button, drawing the line in, and it will say add a new load here. So it's got the position, the action type. At the moment we're going to be using a unit per meter length, but what you can do is create a new load, which maybe if we wanted to do something, so maybe it was 2.3 kilonewtons per meter length, then just add that in, click OK. You can see we've got a green line, and if I solve, I've got a little idea of what it's going to do, but yeah, you can see here now that the result of that is that we've got a yield line underneath where that line load is being applied, as well as the sort of more traditional sort of fan type mechanism around the edges of it. So you can apply line loading like that, you can apply point loading in a very similar manner, and also if you want to, I've got probably not enough time here to explain it, but in some of our other webinar, the recordings which are on YouTube, we can sort of take loading and move it across a slab in order to simulate the movement of a vehicle, for instance, across a bridge deck. Let's see if there are any further questions. I don't think so. So, I mean, that's brought us basically to the end of the webinar today. So many thanks to Matthew for presenting the majority of it, and thanks to all of you guys for attending. We do hope that you found it informative, and as mentioned at the start by myself, if you do have any further questions that haven't been answered within this webinar, then please do just get in touch with us via info@limitstate.com, and we'll be happy to speak to you in depth about it. Just to say that LimitState SLAB is available to download and or purchase now from our website, which is www.limitstate.com. For users, the people who aren't current users of the software, we'll just get in touch with you over the next few days and get some feedback on the webinar and find out if you have any further questions, or if you think the software will be useful to you. And as hinted, if you'd like to watch the webinar again, or if you do know somebody that might be interested to see it, there'll be a recording available, probably either later on today or early tomorrow morning, and we'll email you with a link once it's available online. Finally, please do look out for our other webinars which deal with both LimitState SLAB and our other software products. We send out event notifications by email in advance of these, and they're also posted on our website at limitState.com/webinars. So finally, I'd like to say thank you all again for listening, and hope to speak to you all again soon. Thanks.